Hello everyone, I am Chakri Cherukuri. I work in the quant research group at Bloomberg. In today's talk, we'll see how machine learning techniques can be applied in the field of quant finance. I'll start with use cases in finance where machine learning techniques can be applied, and then we'll look at two case studies in detail. I also want to talk about promoting reproducible research through these examples. So we'll look at interactive plots running in Jupyter notebooks. Notebooks, as you know, are an excellent way of sharing your research, code, and documentation. And interactive plots where we can tweak different parameter settings or test our models over different time periods can really help us identify areas where our models are doing well and areas where our models need to be improved. So first we'll look at datasets involving machine learning use cases involving structured datasets. These are mainly based on financial time series. So time series prediction is an important task. So we have classical techniques which are based on time series analysis like ARMA and GARCH models. But now we can use deep learning techniques like LSTMs, for example, for doing time series predictions. And we'll also look at a use case where we can build systematic trading strategies using machine learning techniques. And dimensionality reduction is an important use case where we have classical techniques like PCA, but now we can use deep learning techniques like autoencoders. Let's now look at unstructured datasets. These are also called alternative data sources. They're becoming very important in both investment industry and in the financial services. So object detection using satellite images and geospatial datasets are now possible thanks to convolutional neural networks. And at Bloomberg, we generate a lot of news articles. So we have teams looking at abstract summarization of news articles using attention-based models. And computing the social sentiment score from news stories and tweets is also an important area where we can apply classical NLP techniques, and we can also use word embeddings and deep learning models. Let's now talk about some of the challenges we face when applying machine learning in finance. Since most of the tasks are supervised machine learning, the first step is to get labeled datasets. In models where there are financial time series, this process is easy because the labels are most often based on future prices or future returns. So they're very easy to build. But unfortunately, on the unstructured datasets, this is a very manual and tedious process. Examples like financial tagging all the financial documents, or going through news stories and tagging them based on the sentiment as negative or positive. All these are very manual processes, and typically companies like Bloomberg, we outsource to vendors like Crowdflower or other vendors. And one important thing is we cannot take these datasets for granted. These labeled datasets, especially if they are built by outsourcing companies, it's important to have a second set of eyes to go through these datasets. And that's why the QA process, when especially alternative data sources are involved, is kind of high compared to datasets which are based on financial time series. When it comes to predictive power, the models which are built on financial time series tend to have low to moderate predictive power. The main reason is financial time series are notoriously non-stationary. So the distributions are constantly changing, and models which are trained using historical datasets may not generalize well when deployed in the future on the test datasets. So let's now look at some use cases. The first example I have is factored strategies using machine learning techniques. A quick primer on factors, or they're also called smart beta. So investors typically think in terms of factors when they make their investment decisions. They do not think in terms of single name securities. So factors are the drivers of risk and return. Factors can also help investors better understand their portfolios, right? They have a common language to talk about, and by thinking in terms of factors, you can better manage your risk and also improve your profitability. The problem with single factors are that they tend to be cyclical in nature, right? They have periods of performance and underperformance depending on different time periods, and these time periods vary for different factors. So investors typically blend these single factors to create multi-factor portfolios. So here we have some canonical ways of combining them. One simple but effective approach is to allocate equal capital to all your single factors, right? That's called equally weighted portfolio. We can also allocate capital based on the marginal risk contribution of each factor, so that we want to equalize the risk contribution from each factors. That's called risk parity. And we can also use mean variance optimization based approaches, where we want to trade off the risk and reward, right? So we can try to find the portfolio which, for example, minimizes the variance of the portfolio, right? Let's now look at a machine learning approach. So the setup here is we have a set of market variables known at time period t, which are known to have some predictive power. Like we can look at market equity indices like S&P 500 levels, or the volatility index, VIX levels, and we can look at macroeconomic variables, fixed income indices, inflation levels, GDP. We can all choose them as features for our model, and the output label is the optimal factor to invest over the next period. And optimal can have various definitions. For example, we can look at the factor which had the best return over the next period, or we can also take into account the risk by dividing it by the historical volatility to get risk adjusted returns. And now it's very easy to build these labels, because historically we know what factors performed well over the next period. So we can easily construct this label data set, and we'll train a classifier on these models. And then when it comes to portfolio construction, we can either invest all our capital in the single factor which the machine learning model predicts, or we can also create a multi-factor portfolio by using the model predicted probabilities as weights, right? So we look at both those approaches in the example I'm going to show you. I want to talk about an important aspect when you're training machine learning models on financial time series. We need to do what we call a rolling forward training and testing. So for example, let's say I want to make predictions for the year 2000. What I do is I go back 10 years, so let's say from 90 to 1999. I use that historical data for training the model and tuning my hyperparameters and all those things. And I make predictions for the year 2000, which is totally out of sample. And when I move to year 2001, I move everything forward, but I have to retrain and recalibrate the model. That's a crucial step. We cannot reuse the old models because we want to capture all the regimes in our data set, and the only way to do it is to train and recalibrate our models for each year. So we have here I'm backtesting from 2000 to 2018, so we have like 19 models to train. Now comes the fun part. We have a lot of choice of classifiers to choose from. We can start with logistic regression, which is a very simple interpretable model, and which has very few hyperparameters. And we can also use some nonlinear models like random forests and boosted trees. XGBoost is one of my favorite boosting algorithms, but it's slow because it has a lot of hyperparameters. And we can also stack these models because the implementation of XGBoost and logistic regressions are totally different. So we can create a meta ensemble by stacking these and try to achieve a small boost in the performance. Some training issues to consider. The labels are very imbalanced, so we have to do some random oversampling. And for cross validation, because this is time series based data set, we cannot just do random splits. We have to, otherwise will induce look ahead bias. So we want to do time series based splitting. And for metric, because of the class imbalance, we have to use F1 score, right? So XGBoost, as I was mentioning before, has a lot of hyperparameters. And since we have 19 models to train, it's important to tune the hyperparameters. So there are different approaches for doing that. Grid search and random search are canonical ways of doing grid hyperparameter tuning, but they do uninformed searches. So what I mean by that is that they do not take advantage of the previous search parameters to guide them in finding the new parameters. So there are newer techniques which are based on Bayesian optimization. Bayesian optimization gives us an informed search. So it leverages the past values to make guided decisions when it's looking in the parameter space. There are also newer techniques which are recently introduced last year called hyperbanded and a hybrid approach of Bayesian optimization and hyperbanded. It's important to keep abreast of all the latest developments which are going on. They may or may not work on your specific problem, but it's important to know what's happening and read the papers and see if you can implement them. So for my example today, the factors I'm choosing are based on Pharma French research factors. They are available on Kenneth French's website, and they go all the way back till 1980s. So we have a rich representative training data to train our models. And so the factors we have are 6 factors here. So market and all the usual suspects, size, momentum, quality, and all. So it's demo time. You can just okay. So all these examples are built in Jupyter notebooks. So as I was mentioning before, they're an excellent way of sharing your research. And here, for example, I'm explaining how different multi-factor portfolios can be built. As you can see, we can write LaTeX equations and we can totally explain our methodology. So let me run the whole. Yeah. So here I have a nice dashboard where we are trying to compare the performance of various multi-factor portfolios. It's very important when you are building machine learning models to compare them against standard canonical benchmarks, right? So, and also when doing backtesting of trading strategies, it's important to test our strategies over different time periods to see how the models perform over different time periods. That's what I mean by reproducible research. Like you can share this notebook with anyone and they can clearly test different combinations to understand how the models are doing. So let me explain the components of this plot. So this first chart is the time series of equity curves. Equity curves are nothing but the portfolio values. So let's say we invest $100 starting in year 2000, how the portfolio value evolves over time. And here I'm showing you the performance of all the single factors. We can see the cyclical nature of factors here. For example, we can see the momentum crash of 2009. And if you look at the more recent periods, we can see the market factor is totally dominating all the other factors. And here I have the performance, but I'm showing it in a risk return space. So I'm showing the return on the y-axis and the annualized volatility, which is a measure of risk on the x-axis. So ideally we want to be somewhere in this region where the returns are high and the risk is low, right? So we can easily look at the performance of all the factors. We can see that market factor is actually very volatile and it has very high returns. Let's now try to add some canonical multi-factor portfolios. I added equally weighted, risk parity, and global minimum variance. And we immediately see the volatility of these multi-factor portfolios is much lower than single factor portfolios. And that's the reason why we have to blend the single factor portfolios. They tend to lower the volatility. And we can also look at the Sharpe ratios and other statistics in this table. We can see that all the multi-factor portfolios generally have a higher Sharpe ratio, which is nothing but risk adjusted returns over a period of time. But now let's now look at the more recent period. We see that the market factor is even dominating all these multi-factor portfolios. It has a higher Sharpe ratio. So let's finally look at the machine learning probability weighted approach. So here we are constructing a multi-factor portfolio where all the weights are coming from the model predicted probabilities. And we see that overall it has a higher Sharpe ratio than other models. And even if you look at more recent periods, it tends to do well, right? The Sharpe ratio is higher. So these kind of tools are like extremely helpful when you want to compare different strategies in one place. We can select different time periods and we can look at the performance of our machine learning models and compare them with all the other existing models. One last thing I want to, can this slides please. Okay, here we have a nice heat map showing the Sharpe ratio of these strategies and looking at every year, and we can compare all the single factors and then the multi-factors here. We can see the cyclical nature of the single factors in this heat map. You see that during some periods there is underperformance in the market, and then there is some underperformance of some factors, and these periods are different. We can easily verify that here. And overall, when you combine the factors, we tend to have a better Sharpe ratio, and these kind of plots are very helpful in getting a very global picture and trying to understand what's happening. And finally, I did not mention transaction costs. Transaction costs are incurred when we make trades, and it's crucial to take into account transaction costs when you're evaluating the performance. I did not take them into account, and so machine learning models tend to have a high turnover, so it's important to regularize these models. And we can also use transaction cost analysis based approaches, where we try to not trade all the way to the weights which are predicted by the model, but trade somewhere close to that region, right? Okay, so let's now look at our second use case, where we do some text analytics on the financial data sets. So social sentiment is a very important concept for investors, and we can glean the social sentiment from news and tweets. By using machine learning models, we can compute the story level sentiment. Story here is a news or a tweet, and then we can aggregate all the story level sentiments at a company level. Like for example, for Apple, I can compute the company level sentiment score on a daily basis or on intraday basis. The sentiment score is very important because it can be used as a trading signal, right? Investors would like to form long short portfolios where they go long, that is, they buy the stocks which have positive sentiment and short the stocks which have negative sentiment. So let's now look at the classification problem, which is at the crux of this sentiment score computation. So we are given a tweet, and the goal is to predict the sentiment, which can be negative, neutral, or positive. So it's a three-way classification problem. The inputs are raw tweets, and the output is the sentiment label. So the methodology here is we are given a labeled training data set. As I was mentioning before, these labels are manually generated by human readers who go through all the tweets and label them as negative, neutral, or positive. We are given that labeled data set. I think it's 100,000 tweets, and then we split it into training, validation, and test data sets. We train the model on the training data set, and then we make predictions on the test data set, and we want to evaluate the performance. So in this example, I'm going to show you how to evaluate the performance of this model on a test data set. For this example, I'm using bag of words based approaches, where we split all the words into tokens, unigrams and bigrams, and we added some custom features like length of the tweet and other things. And we trained 3 binary classifiers for each label, because it's a multi-class classification problem. We trained 3 binary classifiers for each label. For example, the first model will classify the tweets as negative versus not negative, right? It's one versus the rest, so that's what it is. And the models return probabilities, and we output the label associated with the highest probability. Now we want to evaluate the performance. So obviously the first step is to look at misclassifications. We look at a nice metric called confusion matrix, and we also want to understand the model predicted probabilities. So I'll be showing you a nice visualization called triangle. And finally, recall that these labels are manually generated by human readers, so they can make some mistakes, and we'll see how the dashboard can help us fix some of these data issues. A quick intuition on the triangle visualization. So recall that the model returns 3 probabilities which sum to 1. And the idea here is to visualize them as points inside an equilateral triangle. The location of the point and its proximity to the 3 vertices, which represent the 3 labels, gives some indication of the model predicted probabilities. For example, if you have a point which is very close to the positive vertex, what this means is the model is assigning a very high positive probability right. And all the positive predictions of the model will fall in this region of the triangle, because if we take any point in this region, it is closest to the positive vertex. That means the positive probability is dominating the negative and neutral, and therefore all these are positive predictions. Can we have a computer? So let me show you a nice dashboard. So here we have a dashboard. This is a confusion matrix, and a confusion matrix, what it does is it buckets the results of our predictions into cells based on the actual and predicted labels. So by definition, all the correct classification correct predictions are on the diagonal, right, because the actual and the predicted labels match. And all the off diagonal entries are misclassifications because the predicted and the actual labels do not match. Let me click on this cell here. So here we have 103 tweets for which the predicted label is positive, but they are all tagged as negative by the human readers. So these are misclassifications, and because these are all positive predictions, they fall in this region of the triangle. So each point represents a tweet, and we have 103 tweets here. Let me look at some examples here. So here we have a pie chart showing the 3 predicted probabilities, and because it is a logistic regression, it is a linear model. The coefficients of the model are the feature importances, and the features are nothing but the tokens of the tweet. So we can fully understand how the model is making its predictions. For example, the model is the tweet here is weight watchers sees profit slimmed. So there is a very subtle polarity inverting word slimmed, which is totally changing the meaning, but unfortunately the model looks at the word profit and thinks it is positive. It is not giving any importance to this token slim, which means that we need to take into account these polarity inverting words in our feature engineering, or like when you are building the model. One more example, Groupon earnings results not looking good. Again there is this polarity inverting word not, which happens to be in this trigram. Had we taken trigrams, we would have got this. But if you look at this positive model here, which is classifying the tweets as positive versus not positive, it is giving importance to these tokens like good and look good. It does penalize the word not, but it is not enough. And recall that there are 3 models here. I can get the coefficients of the negative model by clicking on this slice of the pie, and here we have the coefficients of the negative model, which is basically classifying the tweets as negative versus not negative. We see that this negative model does give importance to this token not look, right, but it was not enough to surpass the positive probability. Again, an indication that we might have to do some feature engineering to take into account these polarity inverting words. And oops. So let me click on this cell here, where the model's predictions are all positive, but all the tweets are tagged as neutral, and that is where some subjectivity can come into play, right. What makes a tweet negative versus neutral or positive versus neutral? There is some subjectivity involved here, and that is where human readers can make some mistakes. So let us look at this probabilities triangle to see if it can help us in identifying these data issues. We see that points which are close to this positive vertex are interesting, because the model seems to be supremely confident that these are all positive, because they are very close to the positive vertex. So let me select them using a lasso here, and we are looking at the filtered tweets. Let me read through these tweets for you. Leg Mason upgraded by Zacks to hold. Microsoft sales beat street hopes. Cloud profits up. Allstate profit beats estimates. What do you guys think? Are they positive or neutral? Positive, right? And looks like the model is doing the right thing here. There is a price target raised to 49. There is an upgrade. So all these look like positive tweets, and the model seems to be doing the right thing. And the way we found out these data issues is by zeroing in on these tweets where the model is assigning a very high positive probability, right. So, once we fix these data issues and retrain our models, the performance will definitely improve. I just want to make a small comment on interpretable models versus black box models. For example, I could have used word embeddings which are like financial word embeddings which Bloomberg builds all the time, and then I could have trained a bidirectional LSTM or attention based models and tried to improve the performance of this model, right. But then the interpretability is lost, right. So, logistic regression, as we have seen, is a very simple model, but it is very easy to interpret. We can exactly understand how the model is making its predictions, especially when the stakes are high. For example, in this use case, Bloomberg is selling these sentiment scores to investors as an enterprise data feed. So, investors are making trading decisions based on the outcome of these models, right. So, they want to trust the models, otherwise they will never use such models. So, it is important to understand this trade off, and sometimes it makes sense to go with simpler models which are interpretable compared to like fancy deep learning models. There are actually tools like Lime and Sharpe which allow you to interpret even the black box models. So, we should at least try them out when we are building deep learning models. So, I think these are all the examples. So, that is all I have for today. So, there are abundance of financial data, and there are a lot of quant models already in place. Machine learning can definitely help us supplement or augment some of these existing models. Deep learning techniques can be very helpful when we are dealing with alternative data sources. And finally, Jupyter notebooks and some of the interactive visualizations I have shown here can help us promote reproducible research and literate programming. So, that is all I have. I want to thank you all for attending my talk. Yeah.
Could you talk a little bit about what package you're using to create these dashboards?
Yeah.
And what do you like about it, and is there things you wish it could do that it's not able to do?
Yeah. So, at Bloomberg, when we started using Jupyter notebooks, we used matplotlib, but it was a static plotting library, and this was way back in 2012. So, I started playing with D3.js, which is an excellent JavaScript visualization library. But unfortunately, quants do not understand JavaScript, or they do not want to deal with JavaScript. So, what I did was I worked with we hired some people from Jupyter steering committee, and we created a plotting library in the Jupyter notebook called BQplot, which is open sourced on GitHub. It was developed in our group, and all the visualizations I am showing are all built in BQplot. And one cool thing about BQplot is that it's all Python. So, all the JavaScript interactivity is hidden from the user, and the user just deals with Python. So, that is the nice aspect of BQplot. So, yeah. It only works in the Jupyter notebook, because that is how I get to marry Python with JavaScript. Otherwise, it's using the Jupyter's widget infrastructure. We are able to plug them together. Otherwise, there is no way we can. It has to be a website or something like that.
You need like a backend server for that?
We are leveraging the Jupyter kernel.
Oh.
Yeah.
I have a question about unstructured data. Is it specifically for news platforms, or do you pull tweets from individuals as well?
So, the question is about the Twitter data?
Yes.
Yeah. So, the Twitter data is Bloomberg specific. Like, we wanted only tweets of companies which we are tracking in our universe, like I think 3,000 and odd US equities. And also, we don't take any random sources, because there is a lot of noise. So, we only curate some specific sources and tweet handles. So, there is some lot of work going on. People like working on all these things to get a curated list of tweets. Yeah. That is why I could not share these notebooks because of the data set, unfortunately.
What you were saying about the explainability of the model that we did, is it the customers of Bloomberg that's asking you to explain it, or is it the regulators that want to know?
See, as I was mentioning, right, we sell these sentiment scores as an enterprise data feed to customers. So, customers, for example, get every day a feed saying that Apple's score is whatever 0.9, and they already have some models to build trading strategies, and suddenly they'll say, why should I trust this 0.9 and buy Apple, right? So they want some understanding. So what we do is we write white papers explaining our methodology, which we give it to the clients, and these kind of tools will help and like give them confidence that okay, they are doing the right thing, and maybe we should trust these models and trust the scores more importantly.
So if you use this sentiment score as a factor, so how was that influential compared to other factors that you use?
Again, investors, like for example, the common former French factors like value, size, momentum, they have been used to death, right? Like people have been using them. So investors are looking at new sources of alpha. And that's what alt data or alternative data is very important these days. They don't want to look at, because everyone is looking at time series data sets, right? They're looking at satellite images and tweets. They might have some explanatory power because these are generally done before the earnings season. So investors can get some edge, but again, I don't trade, so I don't know. So yeah.